Do you want to be in my soils video?
Yeah, okay.
Francesca, do you ever think about permafrost?
No, I don't.
Can you tell me what permafrost is? Permafrost. Do you ever think about permafrost? Did you know that it's related to climate and climate change?
No, I hadn't thought of that.
Permafrost is super important for climate, and we're going to find out why. According to the USDA Soil Taxonomy Guidelines, permafrost is a thermal condition in which a material, including soil material, remains below 0 degrees Celsius for 2 or more years in succession. In English, this means frozen soil. This is what actual permafrost can look like. This profile is from a coastal plain in northwestern Alaska, where a series of many different environments has produced some striking features. Permafrost soils cover about 9% of global land area. They're concentrated in Arctic and high mountain regions, though some are also found on Antarctica. Permafrost has such a huge influence on soil properties that in 1997, permafrost soils got their own order, the highest level of soil classification, in most of the major soil taxonomic systems. They're called gelisols in the USDA system, or cryosols in some other international systems. Here is a typical gelisol profile. At the top is the active layer, which thaws and refreezes every year. The active layer typically has a few simple horizons. Here we have an O, A, and BW. Below the active layer is the transient layer, which has cryostructures, or ice structures, like these lenticular ones, because this section switches between being part of the active layer and being frozen throughout the year about every 10 years. Here's what lenticular cryostructures actually look like. Next is the intermediate layer, which often has blocks of soil suspended in ice, appropriately called suspended cryostructures. This is the section where the permafrost table rises and falls over longer decadal to centennial periods. Last is the true permafrost, which has stayed frozen for hundreds or thousands of years or more. Permafrost determines much of the physical and chemical properties of these soils. For one thing, permafrost blocks water from draining out of the soil, so pore spaces are full of water instead of air. For another thing, temperatures are below or close to freezing throughout the year, so chemical reactions happen very slowly. The last thing for this video, at least, is cryoturbation. As the active layer freezes every autumn, the freezing water expands, and as it thaws the next spring or summer, it contracts. Over time, this cryoturbation can mix soils and break up horizons, and it can form cool macroscale structures like these ice wedge polygons when water fills vertical cracks and freezes and repeats over many years. The combination of cryoturbation, which brings organic matter deep into the soil, and low temperatures, which inhibit decomposition, cause permafrost soils to store a lot of carbon. These huge carbon stocks make permafrost a really important element of the climate system, and not just as a passive cog, but as an active player that feeds back into the climate system. There's been some back and forth about whether permafrost will amplify warming or suppress it. That is, whether permafrost will contribute more to positive or negative warming feedbacks. A negative feedback is when some initial input has an effect that reduces the input. Permafrost could behave as a negative feedback for global warming. Carbon dioxide from industrial capitalism causes warmer climate at high latitudes, which expands the areas where a lot of plants can grow and lengthens the growing season. These plants then pull more carbon from the atmosphere into the soil, which reduces warming. On the other hand, permafrost soils also contribute to positive warming feedbacks. A positive feedback is when some initial input has an effect that amplifies the initial input. For permafrost, the most well-known positive feedback is that warming, due to industrial carbon dioxide, simply melts permafrost, which allows all that stored organic matter to decompose and releases stored carbon into the atmosphere. And because melting permafrost is typically waterlogged, decomposition takes place in an anaerobic environment, which produces methane, a much more powerful greenhouse gas than carbon dioxide. This process is fairly well known and is accounted for in climate models, but there are some complementary feedbacks that are not. We said earlier that the growing season is longer, Well, this means that the decomposing season is longer too. So it's not just that there's more organic matter available to decay. The organic matter also has more time throughout the year to decay. The microbes that are doing the decomposing and respiring are releasing heat, which further warms the local soil environment. Finally, warming and changing climate disrupts the ecosystems that these soils are part of. Fires and changes in vegetation take away the insulation from plants and the overicing that helps keep the permafrost layer frozen. When we balance these different interactions, negative feedback may dominate the permafrost-climate relationship for a while, as plant growth increases carbon sequestration. But positive feedbacks will probably take over within a few decades as they amplify, as positive feedbacks do. Recent studies within the past 10 or 20 years are telling us that there's more carbon than we thought stored in permafrost soils. That's partly because our soil samples have been too shallow to capture the old carbon buried deep in permafrost from intense mixing over long time spans. And many positive feedbacks have only recently been figured out. Some are still being quantified and incorporated into models. One study that compared models with different feedback suggested that the high-latitude terrestrial carbon response to warming can tip from near equilibrium to a sustained source of carbon dioxide by the mid-21st century. So, while few of us live directly on permafrost soils, permafrost degradation indirectly affects us all. Permafrost is part of climate. It's part of the physical, biological, and chemical systems that govern the planet, as well as the political, economic, and social ones that govern people. We've got to understand it better to predict what future climate may bring us, and besides that, just because it's part of the earth we share as our home.